Now, welcome to this particular section. We are going to be doing the cross section for a rectangle. Now, we know our x-axis is given as integral y squared dA, and from our a is equal to our base times our height, which is the same thing as d. Now, if we say dA dd, if we differentiate a with respect to d, we get b. Cross multiply, it means our dA will give us b dd. Now we go back to our equation ixx is equal to integral y squared dA. It then means that our ixx is equal to integral y squared, which is now d over 2, everything raised to the power of 2, b dd. Now this will give us integral d square over 4 b dd. Now we can bring out b over 4 because it's a constant, so we can factorize b over 4 out, which will give us ixx equals b over 4 integral d square dd. Now this b over 4 times, when you integrate d square, you get d raised to power of 3 divided by 3. Now that is plus an arbitrary constant c. It means our ixx will give us bd cube divided by 12. Now I've gotten our ixx to be bd cube divided by 12. That is one of our main formulas. That is our moment of inertia. Now since our y is equal to ixx over zxx, we can get our term for zxx. Now our y is d over 2, which is ixx, which is our bd cube over 12 times 1 over zxx. Now we made zxx the surrogate formula. Our zxx will then give us d in bd cube, that is bd square, 2 in 12, and that will give us 6. So this is the formula for our sectional modulus. And why is this formula for our moment of inertia? It is important for you to know this too. Now welcome everybody. We are going to be dealing with a circle. Now, given already that area of a sector is equal to area of the major arc minus area of the minor arc. Now our a will then give us theta 2 divided by 360 times pi r square minus theta 1 divided by 360 times pi r square. That is the bigger representing the major arc while the smaller representing the minor arc. Now if we factorize, we can actually factorize it out, but let's leave this as theta 2 over 360 times pi r square minus this, because they are going to have the same r. Now if we factorize theta pi r square divided by 360 out, it will remain theta 2 minus theta 1. Now our a will then give us pi r square over 360, or we can take our pi to be 180. Theta 2 minus theta 1 will give us theta theta, that is d theta. Now 180 over 360 is 1 over 2 times r square d theta. Now our dA d theta will give us 1 over 2 times 2, that will give us 1 r square. Now it means our dA dr will then give us r d theta. That is dA will now give us r dr d theta. Now we have gotten that already. Now let's go back to our formula for our moment of inertia. Ixx is equal to integral 2 pi to 0 integral r to 0 of y squared dA. Now ixx will give us integral 2 pi to 0 integral r to 0. Now our y is r sine theta, so this will be r sine theta raised to power 2, while our dA is our r dr d theta. Now this is a complex integral, but we are going to solve it. It's quite simple. Now our Ixx will give us integral pi to 0. We are going to solve the integral inside first. R to 0. R is equal to this r squared sine square theta times r d theta. Now this will then give us integral 2 pi to 0 integral r to 0. Now r squared times r is power 3 sine square theta dr d theta. Now our Ixx will then give us integral 2 pi to 0. Now sine square theta is a constant, we can bring it out. So that is sine square theta d theta integral r to 0 r raised to power 3 dr. Now Ixx will then give us integral 2 pi to 0 sine square theta d theta times, if you integrate r raised to power 2, that will be r raised to power 2 plus 1 divided by 2 plus 1, and that will give us r raised to power 3. Sorry, r raised to power 4 divided by 4. So it's r raised to power 3 that we integrated. Now this is, which is now r raised to power 4 over 4 integral 2 pi to 0 of sine square theta d theta. Now we have brought r raised to power 4 also as a constant out. So it means our Ixx will give us r raised to power 4 over 4 times integral 2 pi to 0. Now we know sine square theta is the same thing as 1 minus cos 2 theta over 2. That is using your trigonometry ratio to prove that. Now this is d theta, and this will give us integral 2 pi to 0. Don't forget your r raised to power 4 over 4 is still out, of 1 divided by 2 minus cos 2 theta divided by 2 d theta. Now this will give us Ixx is equal to r raised to power 4 over 4 times, when we factorize 1 over 2 out, that will be integral 1 minus cos 2 theta d theta. Now this is Ixx is equal to r raised to power 4 divided by 8, which is 4 times 2 times, now if you integrate 1 you get theta, minus if you integrate cos 2 theta you get 1 over 2 sine 2 theta. So everything from ranging from 2 pi to 0, yeah. Now our Ixx will then give us r raised to power 4 over 8 times, now when we substitute, we are going to substitute 2 pi first, we are also going to substitute 0, but when we substitute 2 pi, or let's say when we substitute 0 minus 1 over 2 sine 0, sine 0 is still 0, so let's just leave to the 0. Now if we substitute 2 pi, that will be 2 pi minus 1 over 2 sine 4 pi. Now this is r raised to power 4 over 8. The reason why we didn't substitute the 0 is that when you substitute the 0, sine 0 is still 0, and that will still give 0. That's why we don't need to substitute that. Now this is r raised to power 4 into sine 2 pi minus 1 over 2 sine 4 pi. Now how is our sine 4 pi 0? Our pi here we are using is a radians, and pi in radians is 180. So 4 times 180, that will give you 720, and sine 720 is 0. So that is why that gave us 0. So our ixx will still give us that I raised power 4 over 8 times 2 pi. Now you can see from here, our diameter is 2 radii. It means our radii is diameter over 2. Now substituting it back, it means our ixx is equal to d over 2 raised power 4 times 1 over 8 times 2 pi. Now this will give us d raised power 4 is d raised power 4, which is pi d raised power 4, divided by 2 raised power 4, which is 16 times 4, and that will give us 64, which is our derivation for our moment of inertia. Now we have gotten our ixx to be equal to pi d raised power 4 over 64, but y is equal to ixx over zxx. Now our y is ixx times 1 over zxx, but our y is d over 2, so it means d over 2 is equal to our ixx is, okay, let's still leave it as ixx times 1 over zxx. Now this is d over 2 is equal to our ixx is pi d raised to power 4 divided by 64 times 1 over zxx. Now if we cancel d from both sides, it means our zxx will give us pi d raised to power 3 divided by 32, which is our sectional modulus for a circle. Now I've gotten our ixx to be pi d raised to power 4 divided by 64. We want to do sectional modulus and moment of inertia for a circular tube. Now, since we know that ixx is pi d raised to power 4 over 64, and the circular tube has a larger circle and an inner circle, so it means our ixx will give us pi d raised to power 4 over 64 minus pi d raised to power 4 over 64, where d is your major diameter and your d is your smaller diameter. Now if factorizing pi over 64 out, you get pi over 64 into d raised to power 4 minus d raised to power 4. Now it means our ixx over zxx is still our y. We know this derivation. Now our ixx over zxx is equal to d over 2, which is our y. Now zxx will then give us 2 times ixx divided by d. So it means our zxx is equal to 2 times 2 over d times our ixx, pi over 64 into d raised to power 4 minus d raised to power 4. Now this is zxx is equal to pi over 2 in 64, that is 32 times d, okay, 32d. Now d raised to power 4 minus d raised to power 4. So zxx will then give us pi over 32d into d raised to power 4 minus d raised to power 4. And that is our sectional modulus, why this is our moment of inertia for a circular tube. Now in this section we're going to be doing for an I-beam. I want to calculate the moments of inertia and sectional modulus for an I-beam. Now we are given some parameters in which you can see on the diagram beside the work screen. Now if you bring out the inner circle, our A1, that is if we have to find area of that square, our A1 will give us base times distance. Now the D will give us B if you differentiate A with respect to D. Now it means our A1 is equal to BDD. Now going back to this square, our A2 will give us D times X. But x plus h plus x is equal to b. Look at this. X plus h plus x will give us b. Now it means that 2x plus h will give us b. So our x is b minus h over 2. So now anywhere we see x in that equation, we'll put b minus h over 2. It means our a2 will give us d times b minus h over 2. Now our dA2 dd will then give us b minus h over 2. It means our dA2 is equal to, so it means our dA2 is equal to b minus h over 2 dd. So that is our dA1 and this is also our dA2. Now let's go back to our Ixx formula. Our Ixx here is given by integral y square dA, that is finding inertia for a rectangular beam, minus 2 integral, if you remove those two hollow parts, integral y square dA2. Now our Ixx will give us integral, let's not forget our y is d over 2, integral d over 2 raised to power of 2 dA1. Our dA1 is b dd. So this b dd minus 2 integral d over 2 raised to power of 2. Our dA2 is b minus h over 2 dd. Now it means our Ixx is equal to d square over 4 times b dd minus 2 integral d square over 4 times b minus h over 2 dd. Now our Ixx will then give us, we can bring out b over 4 as a constant, integral d square dd minus 2, we can bring out b minus h over 8 as a constant. It will remain integral d square dd. Now our Ixx will then give us b over 4 times, if we integrate d raised power 2, that is d raised power 3 over 3 minus 2, or let's cut it, b minus h over 4 times, if we integrate this square, you get d raised power 3 over 3. Now our Ixx will then give us b times d raised power 3, b d raised power 3 divided by 4 times 3, which is 12, minus b minus h d raised power 3 divided by 4 times 3, which is 12. Now our Ixx is, if you find the LCM is 12, so this will be 1 over 12 into b d raised to power 3 minus b minus h into d raised to power 3. So this is the moment of inertia for an I-beam given this kind of parameters. Now after finding moment of inertia, we have to find our sectional modulus, and we know that y is equal to Ixx times 1 over zxx, but our y is d over 2. Now this will give us our Ixx, which is b d raised to power 3 minus b minus h d raised to power 3 divided by 12 times 1 over zxx. Now cross multiply, you get our zxx to be 1 divided by 6d, 2 in 12, which is 6, you bring the d down, into bd raised to power 3 minus b minus h d raised to power 3. So it means our zxx is bd cubed over 6d minus b minus h d cube over 6d. You can still leave it as our zxx is bd square over 6 minus b minus h d cube over 6d. So you can use any of these particular methods to solve, and you can still decide to bring 1 over 6 out, which will remain bd square minus b minus h d cube. So any of those three formulas can be used to find the sectional modulus of an I-beam. Okay, welcome to this particular section, and here we're going to be dealing with a hollow rectangular beam. Now you can see I've brought out the diagram where we have our big B, our small b, our small big D, and also our small d. Now you are going to see how we are going to get our moment of inertia and also our sectional modulus from this diagram. Now, since we know Ixx to be bd cube over 12, which is for a normal rectangular section. Now, which is for a normal rectangular section. Now, for a hollow rectangular section, our Ixx will give us the outer cross section minus the inner cross section, which will be bd cube over 12 minus bd cube over 12. We have our bigger b and we have our smaller b, according to the diagram as seen beside the screen. Now our Ixx, when you factorize 1 over 12 out, it will give us bd cube minus bd cube over 12. Now since our y is Ixx over zxx and our y is d over 2. Now when y is d over 2, our Ixx is 1 over 12 into bd cube minus bd cube, everything times 1 over zxx. Now let's make zxx the surgery formula. It means our zxx will then give us 2 in 12, that is 6. Now d times that 6, that will give us 1 over 6d into bd cube minus bd cube. Now this is the same thing as 1 over 6d into bd cube minus bd cube. Okay, now we are going to do for a square in this particular section, and this is like one of the simplest, though is rare before you use application of this particular one. Now we know area of the square is b times b because all sides of the square are equal. Now our dA dB will differentiate a with respect to 1b. Our dA dB will give us b. Now if you make dA to a formula, you get your b dB. Now since Ixx is equal to integral y squared dA, it means our Ixx is equal to integral our y is what? D over 2 raised to power 2. Our dA is what? b dB. Now our Ixx will then give us b square, if we bring out our b out, b square integral b square dB. Now this gives us our Ixx to be b over 4 times, when you integrate b square you get b raised to power 3 divided by 3 plus an arbitrary constancy because it's an indefinite integral. Now our Ixx will give us b times b raised to power 3, which is b raised to power 4, 4 times 3, which is 12. So it means that the moment of inertia for a square section is b raised to power 4 divided by 12. Now since our Ixx over zxx is equal to our Ixx is b over 4 raised to power 12, or we can still leave it. Our y is b over 2, which is still d over 2. Now our Ixx times 1 over zxx is still equal to b over 2. Now our Ixx, or if we make zxx the zero formula, that will give us 2 over b times ixx. Now it means our zxx is 2 over b times our ixx, which is b raised to power 4 divided by 12. Now our zxx will then give us b raised to power 4 divided by 6, when being b raised to power 4. Okay, now in this question, we are given our B to be 150 mm, our D to be 300 mm, and our F to be 6 Newton per millimeter square. As you can see, the question is placed at a section beside the screen. Now we are looking for our M max, and we know that our M max is given by F times Z. Now our M max is given by our F, which is given to be ZF times BD cubed divided by 6. Now that is, sorry, BD squared divided by 6. So our M max will then give us our F, which is 6 Newton per millimeter square, times our B, which is 150, times our D, which is 300 square, divided by 6. Now if we cross multiply that, that will give us 1 times 150 times 300 square. Now our M max will then give us 1.35 times 10 raised to power 7 Newton millimeter. Now in this question, we're given our M max to be this, our F to be, which is our bending stress. Now going back to our formula, recall that M max is equal to F times Z. Now if we make Z into a formula, that will give us M max over F. And we are given our M max already, so that is our maximum bending moment to be 2.5 times 10 raised to power divided by 7. Now using your calculator, you're going to get 3.57 times 10 raised to power 6 millimeter cube. Okay, in this particular section, we are dealing with an I-beam, and I've already proved the formula for you to the formula for sectional modulus of an I-beam to be 1 over 6 into BD squared minus D cubed over D into B minus H. So we are just simply going to slot in the parameters. The parameters as given on the question. You can see from the diagram beside your screen, it explains basically all the parameters are listed on the board. Now after slotting in all the parameters, we then calculate our zxx will then give us, if you use your calculator to calculate everything, it will give us 862,500, which is 8.625 times 10 raised to power 5 millimeter cube in standard form. That will be the answer. Now since our M max is equal to WL over 8, and that same M max is still the same thing as our F times Z, that is our bending stress times our sectional modulus. Now we are looking for our W, which we are going to make the serial formula. Now our W will then give us 8 times our bending stress, which is 165, times our sectional modulus, which we have gotten to be 8.625 times 10 raised to power 5, everything divided by our L, which is Okay, I didn't put the parameter for L. L is 4.0 meters, so that will be 400. Now, using your calculator, you get your W to be 276,000 Newton, which is approximately 280 kilonewton. Okay, in this particular question, we are still working based on the parameters that are given in the question already. We know our bending stress to be 165, our Max is F times Z, and a lot. Now, let's start from Max is equal to WL over 8. And Max is equal to F times Z. So it means our WL over 8 is equal to F times Z, see, because they are both equating to Max. Now this will give us 65 times 10 raised to the power 2 times 5.5 divided by 8 is equal to our F, which is 165, times our Z. So I'm going to make Z the surface formula. And when we make Z the surface formula, that will be 6.5 times 10 raised to the power 2 times 5.5 times 10 raised to the power 3 divided by 8 times 165. Now using your calculator, you get your Z to be equal to 27848 millimeter cube, which is approximately 270.848 centimeter cube. Okay, welcome to this particular question. It's a very simple question. So now let's first start from our Max is equal to W1L over 4 plus W2L over 8, as you can see from the parameters given. Now our Max will give us, from the parameter, our W1 is 3 times 10 raised to the power 3 because of the conversion, times 6 times 10 raised to the power 3 divided by 4, while our W2 is 2 times 6 times 10 raised to the power 3 times 6 times 10 raised to the power 3. Now you can see why I multiply because that's a UDL load. Now that one divided by 8. Now using your calculator, our Max will then give us 13.5 times 10 raised to the power 6. Now, since our sectional modulus is given by this formula, our ZXX will then give us 1 over 6D into capital B D cube minus small b D cube. Now our ZXX will then give us 1 divided by 6 times our D, which is 450, times our capital B, which is 120, times 450 raised to the power 3 minus our small b, which is, I think that 120 minus 24, that will give us 96 raised to the power 3. Now using our calculator, our ZXX will then give us 2.53 times 10 raised to the power 6. Now our Max is given by our bending stress times our sectional modulus, which is F times Z mathematically. So it means that our F will then give us Max divided by Z if you make F the surface formula. Now I've gotten our Max to be 13.5 times 10 raised to the power 6 divided by our Z, which is 2.53 times 10 raised to the power 6. Now using your calculator, our F will then give us 5.3597 Newton millimeter square. Now in this particular question, we are dealing with a cantilever beam, and the first one is at the support while the second one is from a point 1 meter from the support. Now we know our air max will give us our force times distance. So our air max will give us our force, which is 6 times 10 raised power 3 times our distance, which is 2 times 10 raised power 3. So our air max will give us 6 times 2, which is 12, times 10 raised power 6. That will be our air max at the support. Now to get our z is given by b squared over 6. Our z will then give us, so our z will now give us our b, which is 150, times our d, which is 250 square, divided by 6. Now using your calculator, our z will give us 156.25 times 10 raised per 4 millimeter cube. Now our air max is equal to our F times Z, which is 12 times 10 raised per 6. We are looking for our F. We know our Z to be 156.25 times 10 raised per 4. Now if you make F the sort of formula, you are going to get your 7.6 Newton per millimeter square. Now going to Roman figure 2, we are going to apply the same approach. The only difference is that this one is a 0.1 meter from the support. Now air max will give us 6 times 10 raised power 3 times 1 times 10 raised power 3. Now 6 times 1, that is 6, 10 raised power 3 times 10 raised power 3, that is 10 raised power 6. Now our z is equal to b squared over 6. So our b is 150, our d is 200. Substituting that using your calculator, you're going to get your z to be 1.0 times 10 raised power 6. Now since air max is equal to F times Z, we have gotten our air max to be 6 times 10 raised power 6. We are looking for our F times our Z, which is 1.0 times 10 raised power 6. Now we make F the sort of formula. 10 raised power 6 will cancel 10 raised power 6. 6 divided by 1.0, which is 6.0 Newton per millimeter square. So those will be our bending particular points. Now in this particular question, we are still going to follow parameters. I can see using the diagram given, I've exploded some things on the board. Now the first thing is that we're going to find our reaction at A. So to find reaction at A, I'm going to take a moment about RB. Now taking moment about RB, that will give us RA times 4.2 using your total anti-clockwise equal to the total clockwise moment. Now 40 times distance to RB, which is 2.8, plus if you have to convert that UDL load, if you have to find the moment to RB, that will be 1/2. You know you have to convert it to a point load. You multiply by the load, then you multiply by the total distance. Now using your calculator, you're going to get your RA to be 61.667, which is approximately 61.67 kilonewton. Now since we've gotten our RA to be 61.67 kilonewton, if we are to find our RB, we can take, let's say, taking moment about RA. Now if we are to find RB, we'll take moment about RA. Now it means our RB times 4.2 will give us the load, first load, which is 40 times 1.4, plus converting that UDL load to a point load, that will give 1/2 times 70 times 4.2. So using your calculator, you're going to get your RB to be 48.33 kilonewton. So you can confirm your answer using your total upward forces is equal to total downward forces to confirm if your reaction is correct. For example, for your total downward forces, that will be 40 plus 70, which will give you 110. So if you also add your RA plus RB, it should also give you 110 kilonewton. That's the way to confirm if your reactions are correct. Now, since our Mmax is still the same as our reaction moment minus our load moment, now using reaction at A. Now, if we are to use our reaction at A, our RA we have gotten it to be 61.67, while our RB we have gotten it to be 48.33. Now, using reaction at A, our Mmax will give us 61.67 times the distance there, which is 1.4, which is our reaction moment, minus 1/2 times 1.4/4.2 times 70 times 1.4, which is our load moment. Now, using our calculator, our Mmax will then give us 69.92 kilonewton meter. Our Mmax can be approximated to 70.0 times 10⁶ Newton millimeter. Now, using reaction at B, our reaction at B is 48.33 kilonewton. So our Mmax will give us, now our reaction moment. Our reaction moment will give us 40. Yeah, that will be 48.33 times the distance, which is 2.8, minus our load moment, which will give us half times 2.8/4.2 times 70 times 2.8. Now our Mmax will then give us, using your calculator, that will still give us 69.99 kilonewton meter. Our Mmax is still approximately 70.0 times 10⁶ Newton millimeter. So you can see that either you use your reaction at A or your reaction at B, you're still going to get to the same answer, provided you compute it well. Now, since our Mmax is given by our bending stress times our sectional modulus, and we have gotten our Mmax to be 70.0 times 10⁶, our F is 165. Now, making Z the silver formula, that will give us 70.0 times 10⁶ over 165, which will then give us our Z to be 424,242.4242 millimeter cube. Now, which is approximately 424.242 centimeter cube. Now, in this particular question, we have a triangular load, a UDL, and everything. So our Mmax will give us W1L over 8 plus W2L over 6 plus W3L over 4. W3L over 4, that is representing our point load. W2L over 6 representing our triangular load, while the last represents our UDL. Now, since Mmax is F times Z, that will give us our W1 is 3 times 10⁻³ times the distance, 6 times 10 raised to the power 3 divided by 8 for the UDL. Now going to the triangular load, it is 12 kilonewton, which is 12 times 10 raised to the power 3 times the distance, 6 times 10 raised to the power 3 divided by 6, plus that for the point load. Now for the point load, which is W times 10 raised to the power 3 plus 6 times 10 raised to the power 6 divided by 4, because we are not given a weight for the point load, which is what we are looking for. Now we know our Z to be BD square over 6, so I'm still just going to replicate that. Now 3 times 6 will give us 18, 10 raised to the power 3 times 10 raised to the power 3, which is 10 raised to the power 6 divided by 8, plus 12 times 6, that's 72, plus times 10 raised to the power 6 divided by 6, plus 6 times W, which is 6W times 10 raised to the power 6 divided by 4. Now this will give us 8 times our B. Our B from the question is 250 millimeter. Our D is 300 raised to the power 2 times divided by 6 is equal to 18 times 10 raised to the power 6 divided by 8 plus 72 times 10 raised to the power 6 divided by 6 plus 6W times 10 raised to the power 6 divided by 4. Now our W will give us, using your calculator, if you make W the subject of formula, you are supposed to get 10.5 Newton. Now in this particular section, we are dealing with a circular tube, and at the beginning of the tutorial, I've proven the formulas for how our IXX and our ZXX, the formula for finding the moment of inertia and sectional modulus of a circular tube. Now before we proceed, we have to find area of the shaded parts. And we know that area of a circle is given by pi r square. If you leave it in terms of diameter, that will be pi d square over 4. Now, if you have to find area of the shaded part, that will be pi big D square over 4 minus pi small d square over 4, subtracting the larger circle from the inner circle. Now, we know our capital letter D to be 150, our small letter d to be 100. Substituting it, we are going to get our area of shaded part to be 150 square minus 100 square, that's difference of 2 square, so that will give us 50 times 250, which will give us that divided by 4, which is 3.125 pi. Now we have gotten our area of the shaded part to be that. Now since we know that volume is area times height, we know that volume normally is area times height. Now it means volume of the hollow steel pipe will give us area, which we have gotten to be 3.125 pi, times our height, which is so it means our volume is 3.125 pi L when you multiply that. Now our weight is given by 78 kilonewton per meter cube. Now since it's per meter cube, we have to multiply that value by the volume to get our weight in kilonewton. That's why we found our volume. Now our weight will give us 78 kilonewton over meter cube times our volume, which is also in meter cube. Now our weight, which is W, will give us 78 times 10 raised to the power 3 when you convert that kilonewton to Newton, over meter cube, which will be 10 raised to the power 3, everything raised to the power 3, times the volume, 3.125 pi L. Now it means our weight will give us the number 160 pi L, which is, using your calculator in decimal, that will give you 0.4375 pi L. Now that is our value for W. Now since our ZXX is given by the formula pi 32D into D raised to the power 4, capital D raised to the power 4, minus small d raised to power 4. I've proved this formula in the previous section. Now this will give us pi 32 times our capital D, which is 150, into our small capital D 150 minus our small d 100 raised to power 4. Now using your calculator, we are going to z our xxx in terms of pi to be 10,15625 pi over 12. Now our Max is given by our f times our z, and our Max is WL over 8, which is equal to our f times our zxx, our sectional modulus, which is 1015625 pi divided by 12. Now our W is 0.24375 pi L times the existing L there divided by 8 is equal to our F. Our F given in the question is 150 Newton per millimeter square. So that will be 150 times 1015625 pi divided by 12. Now this will give us L square. L times L is L square. Pi will cancel pi from the other side. Using your calculator, we are going to get our L square to be equal to 41666.7. Now we find the square root of both sides to get the value for L, and we are going to get our L to be 20.41. It means our L is approximately 20.41. Now in this question, we're also looking for our W. Now, since Max is given by WL over 8, our Max is given by, we are looking for our W, we don't know it, but we have to convert it, that is times 10 raised to power 3, times our L, which is 2 times 10 raised to power 3 divided by 8. So it means our Max will give us W times 10 raised to power 6 divided by 2 in 8, which is 4. Now our Max is F times Z, and our Max is W times 10 raised to power 6 over 4. Our F is 8 times our Z, which is BD square over 6. Now this is W times 10 raised to power 6 divided by 4 is equal to 8 times our B, 250, times our D, which is 75 raised to power 2 divided by 6. Now our W using a calculator will give us 15 over 2, and 15 over 2 is 15 split in 2 places, which is 7.5.